So, hello everybody, and we will be saying more things about Cyphered surfaces today, and actually also get some topological consequences. So, but first of all I should say that everything that I will say today is smooth, even if I don't say so. So all surfaces, all knots, everything is smooth. Okay, and furthermore, I will be assuming a lot of differential geometry and a lot of topology of the plane without saying anything. So basically, transversality results. So if you have two surfaces in R3, they intersect generically, they intersect in a line. If they don't intersect in a line, you push them a bit, you deform them a tiny bit, and then they intersect in a line. And that line is in itself smooth. Okay, so I will assume such things without saying much more. And also the topology of the plane, which basically means the Jordan curve theorem. So these are non-trivial results, these are hard results, but I will assume them nevertheless. I mean, basically proving them is too far aside. It's just not the topic of this class. Anyway, so let me remind you, so a Cyphered surface for an oriented, so last time I said knot, but equally well it could have been link. I mean, if it has several components, the definition makes sense just as well. So for an oriented link K is a connected oriented surface, sigma in R3, so embedded in R3, such that the boundary of sigma is the knot. And so far the only thing we have is one example. So here is a knot. In fact, it's the trefoil knot. If you look at it carefully, it's in blue, and there is a surface in green. So in fact, sort of it's and it's oriented because, like, if this lobe is green side up and that lobe is yellow side up, then they're connected by twisted bands, which means that they get reversed. So I mean, it's the right, you keep the orientation. And last time we spent some time deforming this, playing around, deforming it, and finding that it is topologically a sigma 1, 1, where in general all surfaces with boundary are always homeomorphic to one of sigma gn, where G is the genus, namely the number of holes, and n is the number of boundary components, or also sometimes called punctures. Okay? So we did it by hand, and I wanted to say that it's actually a lot easier. You could do it, well, if you are willing to rely on known theorems, you could do it much faster. So the known theorem I want you to rely on is the Euler characteristic. So the Euler characteristic of, in fact, any topological space is equal to the alternating sum of the dimensions of its homology groups. And in fact, we've seen this when we talked about Chovanov homology, but it was not while talking about topological spaces. It is also the alternating sum of so if you are able to write this topological space as a simplicial complex, so basically as a gluing of simplices to each other, so then it has finite dimensional chain groups. You can take these simplices as the chains. Then it's again the alternating sum of the dimensions of the chain groups. And in 2D, this is, so in 2D, C0 is just a collection of points. C1 is a collection of lines, of edges. And C2 is a collection of faces. So triangles, or in fact they don't have to be triangular, you can take any simply connected domain to be your faces. And so the dimension of C0 is the number of points, the dimension of C1 is the number of edges, the dimension of C2 is the number of faces, and so this is usually denoted as V minus E plus F, where V stands for vertices, E stands for edges, and F stands for faces. And in fact, in one dimension, the faces drop out. I mean, if your space is just a gluing of these, then it's V minus E. And the one further thing to say is that, so you see, homology of spaces is homotopy invariant. So if you have two homotopy equivalent spaces, they have the same homology groups. They may have they may have different chain groups and definitely different V minus E plus F, V minus E plus F. They may have different V minus E plus F, they may have different V, different E, different F. In fact, one might be 2D and one might be 1D, but so long as they are homotopy equivalent, the first formula tells you that their Euler characteristics are the same. So all of these are homotopy invariant, and what I mean by that is that if two spaces are homotopy equivalent, then they have the same Euler characteristic. So now, what is the Euler characteristic of a genus G Riemann surface? So if you have a surface of genus G, well, you can compute, basically, one way or another, you divide it into, or you write it as a gluing of vertices and points and edges, and then you can compute that the Euler characteristic is 2 minus 2G. In fact, you can do it in the most minimal way possible. So, I mean, there is a way to present such a surface using one vertex, one face, and 2G edges. Okay? But at any rate, you get 2 minus 2G. And then, I'm hoping you've seen this before. And the Euler characteristic of sigma Gn, G comma n. To get sigma Gn out of a surface of genus G, all you do is you remove n faces. Right? You make n pieces of boundaries, so you remove n faces. If you remove n faces, then f reduces by n, and so the Euler characteristic decreases by n. So this will be 2 minus 2g minus n. Okay? So now, suppose I want to find the Euler characteristic of the surface, suppose I want to find the genus of the surface I started from. So this surface, topologically, so this one is homotopy equivalent to the following. So basically, put a vertex here, put another vertex here, and connect these vertices with 3 edges, one going through each one of the twisted bridges, and then clearly the surface retract to this graph. You can, right, you can shrink all the bands to this graph. So this is homotopy equivalent to a tetragraph. A tetragraph has 2 vertices, so V is equal to 2, and 3 edges, so E is equal to 3. And so the Euler characteristic in our case, so the Euler characteristic of the thing that took us a long time to study can now be computed very quickly. So the Euler characteristic is equal to, what was it, V minus E, so 2 minus 3. So 2 minus 3, I believe, is negative 1. And I want to write it as 2 minus 2g minus, okay, what's the number of holes, of punctures? Well, it's the number of boundary components. Since we started from a knot, the knot is just one component. Had it been a link, it would be several components, but the knot is one component, so this is 1. And now I truly, genuinely hope that I didn't mess anywhere, because I should get that the genus is equal to 1. I think we do get that the genus is equal to 1, yes. So the genus is equal to 1, which is what took us much more pain to do last time. Okay, good. Questions, comments? Okay, so the next thing is I want to prove a theorem. So, theorem, every k has a sigma, and you know, since our notation is fixed, it's clear what I really mean. Every smooth-oriented knot in R3 has a connected, smooth-oriented surface in R3 whose boundary is that knot. Okay? And, okay, so proof, well, I'll give you 2 proofs. So proof number 1, so this is the classical proof. So this is the proof that everybody knows, and it uses sort of, use so-called Cyphered cycles. So I'll do it for the trefoil, but the proof will work equally well for everything. So in fact also for links. So here is the trefoil. Okay, and what you do is, the first step is you replace every crossing. So wherever you see a crossing, you replace it by its oriented smoothing. So remember when we talked about the Jones polynomial, every crossing can be smoothed in 2 ways. But we will use the one which respects the orientation. So in our case, it's the one that looks like this. Okay? The other one, gives you a non-orientable one manifold if you use it. So right, you'll have 2 outgoing arrows on one edge and 2 incoming arrows on the other edge. So this is the one we don't use. Okay? So in our case, what it means is that we get this, we get this smoothing here, this smoothing here, and this smoothing here. Now doing this but keeping the edges of the knot, we get two cycles, and the two cycles are oriented because they inherit an orientation from the knot, and we made sure not to spoil that. So we get two oriented cycles. In our case, the picture is drawn here, but you know, since it is a bit cluttered, maybe I'll shrink it, move it to the side, and make a second picture which hopefully will come out less cluttered. So I have sort of a rounded triangle in the middle, and around it a thing like this. Good. So the second step is to so these things are called the Cyphered Cycles, and there are two of them. So these are the Cyphered Cycles. And the second step is to write each Cyphered cycle as the boundary of a disk. So place, wrong color. So place as many necessary. So place disks in R3 with boundary or boundaries, the Seifert cycles. Now, one disk in this picture is obvious, namely it's this one. The other disk, well, basically if you have nested cycles, and in general the nesting could be worse, right? You could have had, I don't know, lots of Cyphered cycles, and they could be nested in a complicated way. What you do is the innermost one you put first, and then the outer one you put behind. So so here I have two disks, and one is above and hiding the other. Okay? Now, one extra comment. So I actually don't want to think of these disks as being flat. Okay? What I want to do is to kind of let them drop vertically to the back and only then become flat. So when you look at it from the side, they look like bowls. So here is a bowl, and the disks sort of, if you have a cycle, this is a cycle, the disks drop to the background a little bit and then get flattened and then become flat, and so they look like, again, like bowls. Or maybe like mugs, but sort of, okay? Okay. Now, so in other words, when you, well, okay. So now the next step, is to, wherever there used to be a crossing, so wherever there was a crossing, put a twisted band. So, in other words, connect the rim. So, for example, here there used to be a crossing. So, connect the rim of the disk behind to the rim of the disk in front with a twisted band. So a twisted band. So a twisted band looks like a crossing, but it's filled in with surface material, with green material. Okay? So, in fact, sometimes you're going to have a situation like this, where the Seifert surface looks the way I said, and the crossing, no, you'll never have that. Sorry, for orientation reasons, you'll never have that. Sorry, I take it back. So, but basically, this is it. We're done. You've generated the Seifert surface. So, the Seifert surface is the union of all the disks with all the twisted bands. The boundary is, well, I mean, you can just visually see it. It's clear. It's there. Okay, and and it clearly works for every knot. Okay. Good. So, any questions or comments?
So, will every Seifert surface be like? Will every surface be from this kind of way, or?
No. I'll tell you in a second why not. Maybe I should say, why is this surface oriented? So basically, it inherits an orientation from its boundary. So the Cyphered cycles are oriented, they're just disks, and you orient them so that their orientation will match with the orientation of the boundary. And in practice, it means that the counterclockwise cycles get colored white, and the clockwise cycles get colored black. And then every twisted band connect, you just have to check locally that they respect the orientation, and they do. Okay? Now to answer Jessica's question, so clearly I can make surfaces that do not come from this construction. For example, I can take this surface, drill a hole in it here, drill a hole in it here, and connect these two holes with a tube. Okay? This surface has nothing to do with the original knot. I just created a completely useless tube. But it's a legitimate surface. Okay? Good. So here is a second construction. So, a second proof. So, proof 2 is by induction on a knotting number. On the I misspelled something. On the knotting number. So what's the knotting number? It's the number of crossings you have to flip to get to the knot. In general, it's very, very, very hard to compute. It's very hard to tell. If I give you a picture of a knot, it's very hard to tell what is it. It's a knotting number, but it's a number, it exists. Okay? So, if this number is equal to, I don't know, maybe I should call it U for a knotting number. So, if U is equal to 0, then the knot is the knot. And then sigma will be, you just take the knot and put a disk in it. So that's easy enough. Now, suppose, so to prove the induction step, all you need to show is that if K has a Seifert surface sigma, and K prime is obtained from K by flipping one crossing, then we can find a sigma prime. Then we can find a sigma prime such that the boundary of sigma prime is equal to K prime. Okay, so we just have to show that if there was a surface and we flip one crossing, we still have a surface. So let me draw the picture. Okay, so but I want to draw it, it will be a bit confusing. So here is K. K has two strands which I'm about to flip. But you see, I don't want to view the I want to view the crossing from the side. Okay? So you really should be thinking of these two strands as if one is going this way and the other one is going that way. Let me bring it closer to the camera. Okay, so they're both diagonal. Okay, I mean, they're both. So this one is going from the front of the from the front of the screen to behind the screen, and this one is going from behind the screen to the front of the screen. Okay? And furthermore, they are you know what? Maybe it's even easier to orient them in opposite ways. Yeah, it's a bit easier to orient them in opposite ways. Furthermore, let me assume that they are oriented in opposite ways. Now, all this means is that I should be, when I choose which direction to look from, I'll choose the direction from which they will appear to be oriented the opposite way. Okay, if I have a crossing, I can always look at it from some direction so that they will, basically, if the crossing looks like this, I want to look from here so that one appears to be going from left to right and the other appears to be going from right to left. So this is the picture. Good. Now, there is a Seifert surface for K. The Seifert surface has a boundary, this picture. Now, locally, so, you know, this whole picture is very, very, very small. So this thing is happening in some very small part of R3. So, so locally I have the surface approaching this line and approaching that line. And you know, if the surfaces if the surface was approaching from this direction, say, I'll just push it so that it will approach from below. And for the upper line, if it was approaching, I don't care from which direction, I'll just push it around, bend it, so that it will approach from above. So locally, you see, now I just learned that even paper can write on this screen. So locally, I can assume that the top surface looks like this, and the bottom surface looks like that. And now I want to create a surface for the thing that I get when I flip the crossing. Okay? So that, fortunately, is very, very easy. All I have to do is to make two gaps in each line, keep the bulk of the surfaces exactly the same, but add two twisted bands in between, along with pieces of the surface. And now I got a surface, and its boundary is the thing you would see if you flip the crossing. So I believe this proves the theorem.
Hi.
Yeah.
So in the last picture, are we looking at just one crossing or so many crossings? Because I see that you put two twists.
Yeah, but you know what? No, but again, remember that I should be looking at it from above, right? This is a sideways picture. From above, there is only one crossing here. If I was looking, if my eyes was like, as this arrow is showing, right? Because the whole picture was a picture of a crossing from the side. And now, so this is a picture from the side. So if you want to compare it with this, you have to look from above. And when you look from above, there is only one crossing. Okay?
I'm talking about you. So in the band, don't you put only one twist? I see two twists.
Yeah, I put two twisted bands. But two twisted bands make make one crossing when you look from above again. I don't see where you see where I've put two twists. Sorry, I've put two twisted bands, one here, one here. I don't know what are you. Something still bothers you.
Yeah. So in the construction of the Cyphered surface, so after smoothing the crossings, we put a twist in the band.
That was the first construction.
Oh.
This is the second construction.
Oh, okay, thanks.
Okay. So, by the way, okay, so now that we know that every knot has a Seifert surface, we can define, so definition, G of K, or the genus of a knot K, is the minimal genus of a Seifert surface for K. So two very, very minor observations. So I don't know if I should call it not theorems, let's call it an observation. So observations, first of all, K is the A-knot if and only if the genus of K is equal to 0. So if K is the A-knot, then it's the boundary of a disk, and a disk is of genus 0, right? Because it's a sphere with a disk removed. And if the genus is equal to 0, then it means that the knot is a boundary of a disk. And if it's a boundary of a disk, then, oh my god, embedded disk, right? Sorry, so if it's the boundary of an embedded disk, then you can contract it along this disk until you shrink it to nothing. So it's the A-knot. So that's obvious. And the second comment is that the genus of a knot is always less than or equal to the A-knotting number of the knot. Because you can check that the construction I made here, actually, what does this construction do to the Euler characteristic? So really, if this was a face of the original Seifert surface, and this was a face of the original Seifert surface, I could put a vertex in the middle of each one, and then this construction really adds two edges to the graph that you can contract the surface to. So it subtracts 2 from the Euler characteristic, which means it adds 1 to the genus. So basically, every additional crossing you need to flip adds 1 to the genus, and so the genus is less than the annoting number, is at most the annoting number. Okay? Good. And now comes the big theorem, which I doubt we will have time to prove, but here is the big theorem. So the genus of the direct sum of the connected sum of two knots. So I'm not sure what notation I used for the connected sum before, but let me remind you what it is. So if you have K1 and if you have K2, the connect sum is what you get where you just connect them by an extra edge. Okay?
You can use the hash.
I might have used the hash, but I think I want to use plus now. Okay? So the genus of K1 plus K2 is equal to the genus of K1 plus the genus of K2. And even before, so I mean the proof is kind of very nice topology, but even before, a few corollaries. So, you know, we have this addition operation on knots, and it's clearly commutative, clearly associative, right? I mean, if you add 3, it's clearly associative. It clearly has an identity, namely the unknot is the identity. Or, you know, said in formulas, 0 plus k is equal to k, and 0 is both the 0 of the group and the picture of an unknot. So maybe if it had inverses, it would be a group, right? But unfortunately there are no inverses. So corollary is that the space of knot isn't a group as if you have the following. So if K1 plus K2 is equal to 0, so if K2 is the inverse of K1, then both of them are equal to 0. So in fact, the only invertible knot is the unknot. Okay? And why is this? So if K1 plus K2 is equal to 0, then, so now I'm proving that the corollary, so the proof is in purple. If K1 plus K2 is equal to 0, then the genus of K1 plus K2 is equal to 0. The genus is always a non-negative integer, and by the theorem, this is equal to the genus of K1 plus the genus of K2. So if a sum of non-negative integers is 0, it follows that each of them is equal to 0. So the genus of K1 is equal to the genus of K2 is equal to 0, and so both knots are 0. Okay? So, I mean, I haven't proven the theorem, but if I have proven the theorem, once I will have proven the theorem, I will know that the only invertible knot is the unknot. Corollary 2. So, maybe before that, I think I stated it, but let me nevertheless state it again. So, definition, a knot K is prime. So we say that a knot is prime if whenever you write K as the sum as two knots, whenever you write K as the sum of two knots, one of them must be trivial. Okay? So this implies either K1 is equal to the A0, and in that case, of course, K2 will have to be K itself, or K2 is the A0 and K1 is K. So basically, now it's a bit sad that I'm using additive notation. Basically, a knot is prime if it's only divisible by 1, except now it's with additive notation. By 1 in itself, sorry. So anyway, now I can state corollary 2. So a knot of genus 1 is prime. So in particular, prime knots exist. Okay, that's not a priori obvious. And the proof is completely obvious, right? Because the only way to write 1 as a sum of two integers, two natural numbers, is 1 is equal to 1 plus 0. So one of the factors must have genus 0, and then that factor is the A0. Okay? So this is obvious, and in particular, since we have already shown that the trefoil knot is of genus 1, actually we've shown a Cyphered surface of genus 1. So that only shows that its genus is less than or equal to 1. But the genus of the trefoil is not equal to 0, because if it was 0, it would be the trefoil would have to be trivial. And we know that the trefoil is not trivial because we've computed its various invariants, and they're not trivial. It has 3 coloring. Okay? So anyway, in particular, the trefoil is prime. Okay? And the last corollary, corollary 3, every knot can be decomposed into primes. Okay? So every K can be decomposed as a sum of primes. You know, really, I'm sorry for the notation. It really means product of primes. Okay, it's the analog of product of primes. So later we will show. So we haven't yet shown it yet, and this is a lot harder. But later we will show that this decomposition is unique, just like the integers, up to reordering the factors. Okay? So later we will show that it's unique, but for now we just show that it's that it can. So basically, the proof is really easy. So suppose you have K. If it's the proof is by induction on the genus, but I'll show it informally. So suppose you have K. If it is prime, stop. If it is not prime, it means that you can write it as K1 plus K2. Each of these has smaller genus because of the theorem. So each of these has smaller genus, and the theorem was already proven for those. Or said differently, if these are prime, you stop. If they're not prime, you further decompose, and the process is guaranteed to terminate, again, because of the additivity of the genus. Right? Because you can only decompose the genus finitely many times. Okay. Questions, comments?
Yeah, question.
Yeah.
So about the genus and the prime. So a particular projection of So another projection of the trefoil net can have maybe say genus bigger than 1. And so how do you...
No. The genus is the minimal genus of a Seifert surface. So yes, the trefoil has Seifert surfaces of higher genus. For example, you can always take, we do the trick that we did before. So take the Seifert surface of genus 1 and just add tubes to it. Just add handles with no reason, and you can make the genus 70. But the genus is defined to be the minimal genus of a Seifert surface. Okay? Good. So now we can start proving the theorem. So proof of theorem, and unfortunately we're not going to finish it. But you know, again, let me emphasize that this is modulo all of differential geometry. So, well, not all, but modulo lots of differential geometry and topology of R2, so the Jordan curve theorem, essentially. Okay? So, but all of this will actually come in the second side, so let's do the easier side first. So I will first of all prove that the genus of K1 plus K2 is less than or equal to the genus of K1 plus the genus of K2. And this is sort of obvious, but only sort of. So, how should I do that? So, basically, suppose you had sigma 1 and sigma 2 for K1 and K2. So, suppose you had sigma i's, so sigma I, whose boundary is Ki for I equals 1 and 2. And suppose the genus of sigma I is equal to the genus of Ki. So this is not a trivial assertion, right? The genus of Ki is the minimal genus of a surface, and the genus of sigma I is the genus of sigma I. So really I'm saying sigma I minimizes the genus. It's not just a Seifert surface, it's a Seifert surface of minimal genus. So now I want to construct a Seifert surface for K1 plus K2. Okay? So I have K1 and I have K2, and each of them has a surface, and sorry for the very schematic drawing. Now, how do I make the connect sum? I pick a curve connecting the two surfaces and replace it by a little narrow bridge, and that's it. That's the connect sum. So all I have to do is to fill the bridge with make the bridge a band, and you can check that the genus of the newly created surface. So this creates a new surface sigma. So sigma is really sigma 1 union sigma 2 union a band. And you can check that it's genus. I mean, you basically just added two vertices and an edge. So you can calculate the genus, and the genus is what you want it to be. Sorry, is this what you've added? No, you've just... Well, I don't know. You can calculate the genus, and it's what you wanted it to be. Okay?
You've merged two faces and added an edge.
Yeah, I've yeah, okay. All right. So the Euler characteristic doesn't change. That's the point. Anyway, there is only one disturbing issue. So can you guarantee that this line we started from will not intersect these two surfaces? So, you know, I've drawn the picture schematically and I pretended that the surface is as shown. Somehow it's bound by the knot. But what if the knot is really something small in the middle and the surface somehow surrounds it in all directions? Maybe the surface is somehow, I mean, I don't know anything about the surface. I mean, the surface constructed from the Seifert algorithm will not be like that. But I don't know where sigma 1 came from. Sigma 1 came from, maybe was created by somebody evil who made it to surround the K1. So I leave it as a question to you. So how can you guarantee that this doesn't ruin our proof? And I'll answer it on Monday. So I'll quit for now and see you on Monday. Questions, comments before I quit? Okay.
Yeah,
I've got a
actually,
question.
Sorry, yeah?
yeah, I just want to, just a comment that the second knot looks like a swimming duck.
Yeah, you're right. I have nothing to say. That wasn't intentional.
I've got a question about homework 8.
Yes? You know what, I'll
So
turn
the
off the
second
video. You know what, no, let's keep the video on, yeah?
For the second question, is the Alexander quandle always the conjugation quandle within a conjugacy class of some group G?
Yeah.
Are we requiring that we're restricting to a single conjugacy class?
No.
Like, would it be okay if we found
No.
subgroup
No,
and
no.
restricted to like these 4 conjugacy classes?
Yes, so yeah, you are right and I stand corrected. I meant, yeah, I mean, you're right. It doesn't have to be the conjugacy class of one element. It could be a union of conjugacy classes. I'll fix it, I'll change it.
And does it need to be a conjugacy class? Because it would seem a priori that there could be conjugation closed subsets of a group which are not.
No, but that's exactly the point. I mean, every conjugacy closed subset is a union of conjugacy classes. So really what I meant is a conjugacy closed subset.
That's not like immediately true, is it?
Of course it's immediately true.
Because conjugacy closed just means it's closed under conjugation by elements of that subset.
Oh, no, I meant, yeah, you're right. Conjugacy closed by conjugation of the whole group, by the whole group.
Okay.
Yeah.
So it's not just like a subquandle of a group conjugation quandle.
No.
It's specifically one arising from some union of conjugacy classes.
Yes.
Okay.
Okay.
Thanks.
Good. So again, see you on Monday.